to record it.
There you go.
Thank you very much. Good morning, everyone, and welcome to the Monitoring and Modeling Cryospheric Exchange session, part 1. This session is in 3 parts. This is the first one, continuing today afternoon at 2:55 and 4:55 p.m. Eastern Time. So my name is Homa Khairulapur. I'm assistant professor at Wilfrid Laurier University, Waterloo, Ontario, co-chairing this session with Dr. Sean Marshall. So Sean unfortunately couldn't be here today morning, so I'll chairing the session now. I'm talking to you today from Waterloo, Ontario, and acknowledge that Wilfrid Laurier University and its campuses are located on the traditional territory of North Roll, Anishinaabe, and Haudenosaunee people. Also situated on the Haldimand Trace, the land promised in 1784 to the Six Nations of the Grand River. For this morning session, we have 7 oral presentations and 1 poster presentation. Each oral presenter will speak for 10 to 12 minutes and 2-3 minutes for Q&A. The poster presenter will speak for 5 minutes, and then we can have a short Q&A. But there is a separate poster discussion session that you can all attend and ask more questions and have more discussion there. Because the program is packed, I would like to ask our speakers to keep the time. I'll send a notification of 5 minutes and 2 minutes to your chat. Speakers, please keep your eye on your chat while presenting. Thank you. To our audience, if you have questions, please raise your hand, or you can chat and write your question in the chat. Without further ado, my pleasure to invite our first speaker of our session, Brianna Lane. So we'll present Changing Arctic Snow and Ice in situ monitoring using digital camera imagery. Brianna, floor is yours.
Thank you so much. I'm just going to share my screen. Okay, can you see this okay?
Yes, look great. Thank you.
Perfect. Thank you. Okay, hi everyone. My name is Brianna Lane, and I'm a master's student studying under the supervision of Dr. Laura Brown at the University of Toronto, Mississauga. And today I'll be talking about my preliminary master's research that looks at changing Arctic snow and ice in situ monitoring using digital camera imagery. So for a bit of background information, the Arctic is a rapidly changing system due to anthropogenic climate change. And a part of this change is due to the process called Arctic amplification, which essentially means that the Arctic region is warming faster than the global average. And this warming is leading to a rapid loss of snow and ice in recent years, both in terms of extent and duration. And this is a growing concern because it has a lot of different negative implications. So there's the impact on global climate, different hydrological events, biological processes, and then the human communities that live in the north also face different hazards. So overall, it's critical to monitor snow and ice due to the interconnected nature of the Arctic system. A little bit about lake ice phenology. In the Canadian Arctic, lakes will generally have a brief open water season in the summer months, followed by ice cover. And the main driver of lake ice duration is air temperature. So as a response to global warming, we are seeing shorter lake ice duration, later freeze up, and earlier breakup in the Canadian Arctic. Snow cover follows some similarities to lake ice in terms of the timeline. However, snow cover timing is also changing. So recent trends for the Canadian Arctic show earlier snow on and earlier snow off. Lastly, it is predicted by the end of the century that rain will become the predominant form of precipitation in the Arctic. So how do we study snow and ice in the Arctic? There are 2 broad categories. The first one is ex situ methods, such as satellite imagery and model-based approaches. However, satellite data can be limited by spatial and temporal resolution. And on the other hand, we have in situ methods, such as ground-based observations and field measurements. And then new research is starting to use automated cameras for monitoring snow and ice. So these are ground-based cameras that will generally improve resolution. They're pretty inexpensive and easy to set up. And they can also be an important piece in monitoring snow and ice because a lot of these field sites are often inaccessible and in remote locations. So we are utilizing ground-based cameras to monitor snow and ice within the context of the changing Arctic climate. And today I'll be talking about our progress so far with a couple of research objectives. The first one is developing a method for snow and ice data quantification from this camera imagery, and also looking at recent variability in lake ice and snow phenology. So here's a map of the study area in the Canadian High Arctic. We're looking at 5 different lakes. The first one on the left hand is the Hunting Camp Lake, and then on the bottom right, you'll see Plateau, North, Small, and Resolute Lake. And all 5 of these lakes are less than 2 square kilometers in surface area, so they're small to medium small lakes. And this area itself is a tundra ecoregion, so it is a relatively cold and dry environment. So currently there is an existing camera network set up overlooking these 5 lakes. Pictured here, this is the Reconyx Hyperfire outdoor camera, and we have available images between 2 to 7 years, and the photos are taken twice daily. So last summer in 2021, we started a ground truthing survey at Resolute Lake in order to get some ground control points. That's what's pictured here, and this coming summer we'll be completing the ground truthing survey on the remaining 4 lakes. We also have some snow survey data available from the past few years, which provides information such as snow depth and snow density, and some information on the snow conditions on the lake. As well, we have manually extracted the lake ice and snow phenology dates from the camera imagery. So in this case, when I talk about ice on, it is the first appearance of ice on the lakes, and ice off was when the lakes were completely ice-free. Similarly, snow on was the first appearance of snow, and then snow off was when the lakes were, the terrain was snow-free. So we began by exploring some different software packages in terms of the ability for image analysis, and we are currently using AirDAS Imagine 2020, which is a platform typically used for remote sensing. So once we chose this platform, we had started with a supervised classification, which is an interactive technique for categorizing the pixels, and the user has the ability to provide examples of what each of the different classes that they want to look like. And in AirDAS Imagine, we're using the accuracy assessment, which through a set of points that is sampled through stratified random sampling, these reference pixels are compared to classified pixels. And for us, we chose 100 points for each of our different classes for that. In terms of the kappa coefficient, this is the proportion of reduction in error. So how much better is the computer classification performing rather than random chance? And then in order to validate our results, we are manually digitizing some of the images and then comparing these reference images to the classified images in a pixel-based validation approach. And the reason why we chose supervised classification to begin with is because the training is controlled by the user. So we chose supervised classification since we did have a prior knowledge of the classes that we wanted. However, once we begin to automate this process, unsupervised classification may be more suitable, or some combination of the two. So here is a flowchart of the process that we use for each of these images. So right now we're working on automating this process, as I said, using creating an algorithm in AirDAS to do this, but right now we're just doing this manually. So we start with the pre-processing, so taking off the date and the time from the image, examining image quality, is it suitable for classification, and then removing the banners at the top and the bottom of the image. Next, we georectify the image by adding ground control points and complete the classification process, which I talked a little bit about. And finally, the data extraction phase involves getting the phenology dates and then looking at the spatial cover of snow. So I'm just going to show 2 examples of our preliminary results from image classification. On the left-hand side, you'll see an aerial shot of Resolute Lake, and then the right-hand side is the ground-based camera image that we have, and this was taken in August of 2020. And then this is the supervised classified image. So the blue is the water, the brown is shore, the grayish is background, and then any black pixels are unclassified. And both of the examples that I'll be showing have similar issues in that some of the pixels are misclassified in the sky. So I'll just show this blue here, and then in the top right corner here as well. So one of the reasons in this particular case that could have happened is because of the sun glare in the original image. So just right here. Originally, in the first classification we tried with this picture, this part was classified as snow. So essentially what we did was we created masks to take out the sky, and however, masking out the sky did lower the accuracy of the classification. And one of the reasons we suspect that might be due to the fact that in the wintertime, when there is snow and ice, there's not as much contrast or distinction between the pixels. So we're working on ways around this, and currently what that means is we're reevaluating our signatures, which are the classes that we give to the computer before the classification process. So this is the first example, and then the next example is also with Resolute Lake. Now we just have some snow and ice cover. Apologies. Now my computer's frozen. There we go. Sorry. So this is the second example of the classified image where the white is snow, the blue is ice, the gray is background again, and black is unclassified. So we do have a lower accuracy value and a lower K value in this one. And the computer does have difficulty being able to differentiate between the ice and the snow, as well as between the cloud cover. So similar to the last example, we're working on reevaluating the signatures. And then if that doesn't work, we may have to go back and retrain the classes. So now that I've talked a little bit about the image classification process, this is our lake ice phenology data that we have. So these are all of the study years we have across the 5 different lakes. And in this case, the dotted lines are just meant more as a visual guide. So on the left-hand side, we have ice on, and ice on is typically controlled by lake morphology, so factors including depth. So Hunting Camp Lake, which is the gray line on the bottom, does have an earlier ice on, and one of the reasons it might not be behaving like the other lakes is because it is a bit shallower than the other 4. And on the right-hand side, we have ice off. In this case, we do see a better synchrony between the 5 lakes, and breakup is more climate controlled, so factors including temperature and wind will be factors driving the ice off date. To note for the right-hand graph, North Lake and Plateau Lake are only represented as single data points in 2020 because unfortunately we did miss the breakup in 2021. So these are the same graphs, just instead of color coding them by lake, it's just all of our data points. And this is just to show that the mean ice on was September 11th, and then the mean ice off was July 31st, but we don't see any clear patterns in our short-term data so far. So now these are the snow phenology dates that we have. Again, these were manually extracted from our camera imagery. And surprisingly, there was a wide variability in the snow on date. A couple of different factors for that could be the camera direction as well as the wind redistributing the snow. In terms of snow off, there was little variability up until 2020, and then a wide variability in 2021. So we'll have to take a look at the snow surveys we have from this year to get a better understanding of why there was such a wide variability between our 5 study lakes. In terms of ongoing work, once we've reached a satisfactory level of our image classification process, then we'll be completing that for the remaining images and for the remaining 4 lakes. We'll be continuing the analysis of recent variability. So I did talk a little bit about the ice on and ice off and snow on and snow off, but we're also going to be looking at the rates of melt and freeze and then the snow cover redistribution visible in the camera imagery. And once we have a good understanding of this observed variability, we'll be placing it into context of existing long-term records that are available. So there is climate data available from 2 nearby weather towers, as well as ice phenology dates from the Canadian Ice Database for Resolute Lake. In terms of the significance of this project, we are working towards improving methods for physical geography, specifically using these automated cameras, looking to develop a practical and accessible way of classifying these images, and then that can be applicable to other subdisciplines in physical geography. As well, we're determining spatial patterns to provide better understanding of the current snow and ice conditions in the study region. And hopefully by understanding the current snow and ice conditions, these can be used for better projections for the future under changing climate conditions. So thank you very much for listening. And at this time, I'd be happy to take any questions.
Thank you, Brianna, for your great presentation. So we have time for questions. Please raise your hand or write in the chat if you have any question. So Brianna, while our audience are warming up, so I have a couple of questions for you. The first, you said that you taking images pictures on 2 times per day, is that right? Mm-hmm. And are they sending to you by like a radium system, or it's based on that?
Unfortunately, no. So we have SD cards in the cameras that are storing the images, but we were looking at adding being able to send the photos back here, but since there's no cell service at the cameras, we aren't able to do that. So we do have to go and manually download the images.
Have you ever looked at any options in the future that you might deploy any radium system, any cell that might be available there in the future?
I think so. So we were talking about at Resolute Lake, that is the lake that's closest to the town where the cell signal is. So it for some services it works and some it doesn't. So we're looking at having that closest camera being able to do that. And that's also one of the cameras where we have the longest data set since 2017 at least. So it would be better than nothing at least.
Nice.
Yeah.
Very, very good. We do have one question in the chat. Samuel is asking.
Yeah. So in terms of the criteria for this case, I was using snow on and ice on was the first appearance of snow and the first appearance of ice on the lakes. And then snow off was when the landscape was snow free, and ice off was when there was no ice on the lakes. And we also are recording, so what we have been calling like first on and then final on. So once the lakes are completely frozen, that would be like the final ice on. So we do have that information. I just didn't put it in the graphs today.
And one more quick question. When you look at the changes in ice on and ice off over the time, I'm just wondering if you have calculated the rate of change for each lake and look which lake based on the lat, like you might find any relationship between that.
Mm-hmm. I haven't looked at that just yet. Hopefully soon though, just in terms of the rates of melt and freeze. And then also look, we do have some information about the bathymetry of the lakes. And so that will also be good to get a better understanding of which lakes are melting faster, or if they're not, if there isn't a big difference between them.
Perfect. Thank you very much. Oh, we do have one more question in the chat.
And how did I create the ground control points for the images? In this case, so when we went in person, we got the GPS points. We had about 10, I believe. And then through AirDAS Imagine, that's actually how within the program was how I added them to the image. And then we'll be using them in the analysis phase as well. Hope that answers your question.
Thank you. Thank you, Brianna, for the great presentation. So to keep the time, we move on to the next presenter, Lisa Michel. If you don't mind, you can share your screen. That would be awesome.
Hi, so I'm Lisa. I'm a master's student at Université du Québec at Trois-Rivières with Christophe Kinard, and I'm going to talk to you about the comparison of temperature index mass balance model in climate change conditions. So I have trouble. Okay, so there's two types of mass balance models for recreating the changes of glaciers. So there's the physical models that are more complex. They have a good performance for long-term mass balance, and they are able to reproduce well daily and seasonal melt variations. But they do need a lot of meteorological data that are not available on all glaciers. The temperature index model are more simple. They need few meteorological data that are more often available. They have a good reproduction of seasonal melt variations, but they struggle more with daily melt variations. They tend to under-evaluate melt, and their accuracy diminish when they are extrapolated out of calibration conditions. So in previous studies, they assume that when a temperature index model worked well to recreate the variation of the glacier in the past, it will also perform well to project how the glacier will change in the future. And that can be hard to confirm because the accuracy is less good when it's extrapolated. So the goal of this study is to evaluate the temperature index model directly in climate change conditions. So the data from the field is not available because it doesn't exist yet. To resolve this problem, we take the results from a physical model that had projected the mass balance of our glacier in different climate scenarios, and we will use the physical model as the real mass balance data of our glacier. And we will compare a 4 temperature index model with the physical model. We also want to know what are the impacts of the calibration method on the projections. This hasn't really been studied before, so we wanted to see how it affects the results of our models. The study area is Saskatchewan Glacier in Alberta, in the Canadian Rockies. It's part of the Columbia ice field, and the red dots on the figure are the virtual stakes that we are using to compare the models between them. So our 4 temperature index model here. So the first one is the classical temperature index model. It has 2 parameters that we need to calibrate. So there's the degree factor for snow and 1 for ice, and the air temperature. In the second model from Huck, we have a melt factor to calibrate and 2 radiations factor, 1 for snow and 1 for ice. And the I is the potential radiations. So we also need only air temperature from the field. The third model is the same as the second one, but we add global radiation measured on the field, also from UP. And the last model is the enhanced temperature index, where we have 2 parameters to set. So the melt factor and SRF, that is a radiation factor. And the radiation, albedo, and air temperature are accounted for. So the methods of this project are separated in 2 big sections. So first we calibrate the model. So we run them with a range of values for every parameter. And then we compare the projections with the results of the physical model. The goal is to find the parameters values that are closer to the physical ones. So we want to find the optimal values for the parameters. We have 3 ways of comparing the temperature index model with the physical model because we wanted to verify the impact of calibration method. So the first method is to compare the mass balance of the total area of our glacier from the temperature index model with the physical one. The second method, we take the mean mass balance of all the stakes from the temperature index model with the same thing for the physical one. And the third method, we make the mean of the differences between the stakes from the physical model and the temperature index model. That makes a more of a discrimination on the territory. Once we have the optimal values, we also have a set of equifinal values that are, it means that they are statistically as good as the optimal value to recreate the physical model results. So to validate if these parameters values are really good, we make simulations of the temperature index models with these values for 81 climate scenarios to see if they are still accurate in climate change context. So we have, for the climate scenarios, changes of air temperature from 0 to +8 degrees Celsius, and changes of precipitation between -20 and +20%. I have preliminary result to present you. Because of technical problems, I don't have all of the validation results for the models. So here are the calibration results. In color, we have the NSC, so that's the correlations. When in approach 1, it approached perfect correlation between the model and the physical model. The red dots are the optimal values for the parameters, and the black dots are the equifinal values. So we can see that for the first 3 models, the third method of calibration have a distribution shape that is more rounded around the optimal value, that tells us that might be a method that is more accurate to find the optimal values. But we have to be careful, because on the table we can see the number of equiphenol combinations for every method, and there's a lot more for the third method, so it might be less precise. For the validation, I have the figure for the first model. In color, we have the bias between the model and the physical results in different climate scenarios. So on the y-axis, we have changes in precipitation, and on the x-axis, we have changes of air temperature. We can see that the model is more sensitive to changes of air temperature than precipitation. And we can also see that when the changes of air temperature are bigger, the third method have a lesser bias, so it might work better in extreme climate change conditions. Here we have also for the first model, cumulative mass balance. So even if the results are practically the same, it can accumulate over years. So that's the goal of these figures. On the left, we have the cumulative mass balance for calibration conditions, climate conditions. And on the right, we have the same thing, but for the most probable climate change scenario according to IPCC for our area. So the blue lines are the physical model projections, and the bold line are the first model projections for every optimal sets of parameters for the three methods, and the buffer zones are the equiphenol distributions of values for each of these three calibration methods. We can see that in calibration climate conditions, the first two methods gives us parameters that are gives closer predictions to the physical model, and for climate change condition, it's the third method that gives us a more accurate results. So it is hard to make conclusion at this point of the study, because we don't have the results for all models, but we can already see that there is differences in the results when we use different calibration methods. So it'll be interesting to push further on that and to see how it affects the projections, and to see how the results are different between different temperature index models. So thank you.
Thank you, Lisa. Great presentation. So we have time for questions, and the audience, if you have questions, please raise your hand or write it in the chat. I have one very quick question, Lisa, for you. In slide 4, where you showed your city area,
yeah,
there was a red dots that, I mean, in the beginning you mentioned that you don't have any ground truth observations, right?
yeah.
And I was wondering what was, you probably explain it, but I might miss it. So I was wondering what was their points that you showed it over the glaciers.
So the points are like grid cells of my DEM, my digital elevation model. So it's grid points that we use as stakes for the study. So we are able to compare like the same grid points for the temperature index models than for the physical model.
You compared them points with your physical models.
Yeah, for two of the calibration methods, we use stakes mass balance. And so that are these points represent this virtual stakes.
Okay, thank you. Thank you. So we have one question from Muri. Have you looked just at days without precipitation for model fit?
No. So it's not written because the precipitations are not in models equations, but they are used for to run the models, like in the
Good.
I don't know
Okay.
if it answers the question. I'm not sure I understand.
And we have another question from Martin. Do you include for the physical model also turbulence, latent, and sensible heat?
Yes, the physical model is done by Kinar and al. 2022. So I did not work on it, but I know, like, I have all the data, and I know that they use that the Omgren and like, I don't remember. So it's the more complete physical model, and they use turbulent and sensible heat.
Okay, thank you very much. If you have following question, you can always contact Lisa offline. So to keep the time on, so we move on to the next presenter. Our next presenter is Amanda Kotela. So she's presenting comparison and collaboration of the temperature index based coupled glacier mass balance dynamic evolution model. Sorry. Okay, Amanda, over to you. Very great presentation. So for the sake of time, we move on to the next presenter, which is our first poster presentation. So we have Okan Aygan, if I'm pronouncing right. Okan, do you mind to share your screen? Yes. So you will have 5 minutes to
it will take less than that.
Okay, and we'll have a short Q&A. So if audience have questions, but there is extra poster discussion session that everyone can attend. So exactly. Over to you, Okan.
Okay, thank you. I'm gonna okay. I'm gonna share my poster. Do you see it well? Okay, perfect.
Yes.
Okay, hi everyone, my name is Okan. I'm a postdoctoral fellow at the Center for Hydrology of University of Saskatchewan in Canmore at the Cold Water Laboratory. And today I'm briefly gonna take you over my presentation, which is on diagnosing the future hydrology of a Central Asian glacier-ice basin using a hydrological glaciological land surface model. Here, I would like to acknowledge my co-authors as well, John Pomeroy, Martin Clark, and Alain Pietroniro. To start with, water resources in high mountain Central Asia are strongly dependent on snow and glacier melt, and these are vulnerable to climate change. However, how climate change impacts the hydrology in the region has not been really previously diagnosed using physically based glacial-hydrological models that can resolve the mountain snow and glacier hydrology with confidence. Here, with this motivation, in this project, we assess or aim to assess the impacts of projected climate change on the hydrology of snow-covered Alarcha River Basin in the Shanshan Mountains of Kyrgyzstan, which is a mountain headwater basin, and 15% of the basin is covered by the glacier. This is the major basin in the region which provides domestic water supply for the capital of Kyrgyzstan, Bishkek, therefore is quite important. And in this project, the current and future hydrological processes and stream flow were diagnosed using MESH model, which is a Canadian physically based hydrological land surface model. The MESH model here was forced by the EM Earth and ERA5 reanalysis datasets. And also most of the model parameters were transferred from the previous mesh applications in Western Canada, which means that we applied on a limited calibration. And for the climate change impact assessment, the temperature and precipitation forcing data over the 1991 and 2010 were seasonally perturbed using the outcomes of CMOS R5 subset for RCP 8.5 for the region over the 2081-2100 period. Looking at the model results over the historical period, what we see is there's an overall quite well performance of the mesh simulating stream flow, both over the calibration and validation periods, which are at 1990, 2000, and 2000 to 2010. Cleaning the efficiency is over 0.9, and the percent bias is below 1% over both periods. And also looking at snow simulations, what we see is the snow cover area as well as the snow depth simulations are matching well with the observations. And if we move forward for the climate change impact assessments and look at the Ala-Archa River Basin under RCP 8.5 climate in the future, what we see is, although there is a little bit change in the total amount of precipitation, there's a decrease in snowfall ratio by 14% from 48 to 34%. And accordingly, the rainfall fraction increases from 52 to 66%. Looking at the snow water equivalent, there is a decrease by 15% on average in peak snow water equivalent, and snow cover duration shrinks by 2 months. And looking at the stream flow projections, the peak flow shifts from mid-July to mid-June for the future period compared to the historical simulation period. And both the peak flow and the annual stream flow volume declines by 50% if there is a complete disappearance of the glaciers in the region, which is quite alarming. As a conclusion, what we saw is coupling reanalysis products to physically based hydrological glaciological models can provide credible simulation in high mountain basins. And looking at our methodology, the modeling concepts, setups, and parameters can be transferred from research basins to high mountain river headwater basins and downstream basins around the world. And results for this specific basin show significantly reduced future stream flow under climate change, which is primarily due to deglaciation and secondarily due to reduction of seasonal snow cover. And finally, the results underline the need for renewed diagnostic assessments of water supply in high mountain headwaters of Central Asia to actually inform the adaptation to climate change. That's it. Thank you.
Thank you, Okan. We can have one quick question. If you have any question, please ask now. Quick question from me, Okan. Why 2010? Why you are not continuing after 2010? Is it any specific reason for?
We observed this year that we could get stops at 2010.
For validation.
Yeah, it's already hard to find data there. And 2010 is like the last year that we had daily observed discharge data.
Thank you very much. And just for our audience, so we have in our session, part 3 of the session, which is at 4:55 today p.m., the third one, we have a 15-minute gap between the first and second presentation. So we have 15 minutes that I would suggest join in, and our presenter can join in, and we can have a good 15 minutes discussion during that. Good. To move on, our next presenter is Murray Pelto. So he's going to present heat wave impact on glacial mass balance and runoff. Murray, over to you. Please share your screen.
Yeah, I guess I'll start with a little hat tip to Chris Chutko and Craig Smith for their Eastern Snow Conference leadership. You also see this hat is a little bleached out, so I am in need of a new Eastern Snow Conference hat. So this is looking at really the contribution specifically during heat waves of glaciers to the Nooksack River Basin, which is in the northwest corner of the state of Washington, and also looking at the impact on salmon. So co-authors Mariama Dryak at the University of Colorado and Jill Pelto, we spent a number of years in the field on this. So we're going to draw on a couple things. First of all, we have a 38-year record of glacier mass balance, so that is going to quantify that specific response. We have seen a real response of these glaciers to climate change. We're also going to look at the kind of the ameliorating role of glacier runoff on discharge and water temperature, but specifically during these 24 heat wave events that we've seen. We're looking at the 2010 to 2021 period because the USGS had discharge records for a long time, but they didn't put in temperature stream records until 2010. And then we'll talk a little bit about the salmon part of it. So the ideal spot to look, because the Nooksack has 3 forks, we're going to look at the South Fork to the North Fork, really. South Fork has no glaciers, and the North Fork has 6.1% glacier cover. So it's a great place to contrast the impact of any particular weather event, climate event on glacier runoff. So first of all, we have the 38-year mass balance record. 3 of these glaciers we monitor every year are part of the World Glacier Monitoring Service Reference Glacier Network, which means they have 30 years of continuous monitoring. And here you just a comparison between these North Cascade glaciers and the overall global record from the World Glacier Monitoring Service. You can see a very similar trend. So we've lost 20 meters of mass since I began this work in 1984. So one of the concerns is just that when you have heat waves, particularly once the glacier surface is exposed to ice, firn, you really can accelerate ablation. And so we really don't want to see that mass loss. So here's just an example of right below this glacier. We're also where we're measuring ablation and mass balance. We're also measuring stream flow. The Nooksack Indian tribe has put in a gauging station below this glacier, so we have about a decade of runoff records. And so our job was to really generate a rating curve for this particular station right below the Shoals Glacier. So essentially all glacier runoff coming down here. So a good way to spend a summer day getting a little cooled off there. So this is the station the Nooksack Indian tribe establishes it each summer. Some years there's a met station, some years there's not. But the runoff station you can see right there, just kind of in the lower right. And it's just a water level gauge. So we calibrate that water level gauge. 2015, you can see almost no snow on the glacier. Bare ice melts a lot faster. 2016, a lot more snow cover on the glacier. Same day of the year, August 6th, both years in this case. And then 2021, same location. So the study reach where we're measuring the stream flow is a very consistent channel width, channel bed. It's actually some little basalt bed to the stream. So we've already heard from Lisa and Amanda about the DDF. So just during their presentations, I took out a couple slides. So we just have the degree day factor for snow and ice here. This is only based on days where it's not raining. It's during heat waves. So all these days are warm. They're all dry. And so it's very specific to those days. You can see that the DDF for ice is about 50% higher than for snow. So the real issue during the heat waves of late is that when they occur earlier in the summer and they strip away that snowpack and expose the glacier ice, that just accelerates melt. And this is 2021, so here we are midsummer. You're looking up to the top of Mount Baker on the Eastern Glacier. You can see it's 50% bare already, with still plenty of 2 months left in the melt season. And so it's going to have 50% more melt from those bare ice areas than if it was snow covered. Coleman Glacier, same thing. This is a sentinel image from early September. This glacier should be at this time of year 70% snow covered, but instead it's 70% bare ice and fern, which again leads to a lot more runoff. So in other words, you can build just a daily runoff record. We have the ablation data, and we have the USGS streamflow data, and we just multiply by the area of the glaciers to come up with the runoff. And this is from 2015 for every day, but we're only looking at heat waves here. And by heat waves, we're talking about days where the temperature exceeds 14 degrees C at a SNOTEL station that's 5 kilometers away. And what you'll see is that, and there are also periods that extend for at least 5 days in which there's no rain. And you can see that in the South Fork with no glaciers, you have about a 20% decrease every time, or on average. And in the North Fork, you have a 20 to 25% increase during these heat waves because of the glacier melt. Temperature, same type of contrast. South Fork of the Nooksack, temperature goes up by, on average, 2 degrees during a heat wave, whereas the North Fork goes up by maybe 0.5 to 1 degree centigrade. So again, that's the ameliorating role during heat waves. So the glaciers keep discharge high, and they keep the temperature change low. So now let's look at the 2021 heat wave. Obviously very unusual. The most exceptional event we've had in the Pacific Northwest. For this time of the year, Thompson et al. 2022 just showed that there's no other comparable where the temperature goes above 35 degrees C at stations in this region. If you look at the year 5 data for 3,000 meters on Mount Baker, the 5 warmest days of the last 70 are all those 5 days in a row in 2021. Right during that period, there's a lot of snow still in the basin, so it's a little bit different. But you can see the discharge in the North Fork of the Nooksack is going up. South Fork starts to go down a little, rises just a tad, and then starts to diminish. And that's because there's still quite a bit of snowpack. But the temperature signal is about right. The North Fork of the Nooksack, the max temperature you can see at the bottom left, 11 to 12 degrees each day, whereas the South Fork rises, and it rises from about 15 at the start of this period to almost 18 degrees, so a 3 degrees centigrade rise, whereas it was less than a degree in the North Fork. And so why does the temperature matter? This is just a map showing where the salmon are in the various streams. Each color represents a different salmon run. And so Parkinson et al., looking at the Fraser River, has really just looked at these thresholds at 12 degrees C and 19 C, where you change communities. And what you saw is the North Fork of the Nooksack is below 12, and the South Fork is pushing that 19 degrees C, where their community would change. And during heat waves in particular, they're exceeding 19 C in 14 of those 24 heat waves. So the salmon tolerance is going to be impacted. And so here, this is a data series of the salmon in the stream. It's Jill did a painting of this data series. It's got an X and Y axis to it. You can see the salmon have not been recovering. There's a lot of factors that matter to the salmon. They go under the Salus Sea. Some of the salmon are hatchery raised. So all you could say is that things aren't going in the right direction. But overall, we see these heat waves popping up over and over again. And it's not just in the North Cascades. Here's an example, 2018 in the Yukon. Over 4 days, you see from the upper left, there's no snow swamp above the snow line with purple dots. And by June 26th, there's this huge 25 square kilometer area, snow swamp, saturated snowpack. So it's different, has a different effect, but you can really see the heat wave impact from July 2018. Or this winter, January 2013 or 2022. Vulcanavero in Argentina could have picked a lot of glaciers there in the Andes. Bear was still 2 months to go left in the summer. Obviously a really high ablation, going to lose a lot of glacier area and volume as a result. So I guess the bottom line is these alpine glaciers aren't really compatible with heat waves. And so that's my bigger concern. The smaller concern is just in the Nooksack, we're seeing impacts. So thank you for your time.
Thank you. Thank you very much, Murray, for your presentation. So we have time for questions. So please raise your hand. While we are waiting, I can start off. So in one of your slides, you showed the bar chart of runoff rate, which 2020 shows the highest significance compared to other years. And then when you showed the bar chart of temperature change, 2020 was not the only one or highest one. I was wondering what affected the 2020 high rate of the runoff, if it's not only the temperature heat.
So in this basin, this is the USGS record, so it's not just about glaciers, there's also forests feeding into the system. And so it's going to be the preceding period. How much rainfall did you have? And if you're into a prolonged drought, that's going to really affect, the discharge response, but also the temperature response a bit. So these are looking during the heat wave, what changes from the start to the end. But how much, how long the dry period, or if you had rain right before then, is going to change that response some.
So although the 2020 was not the year of the highest heat wave, so there was probably precipitation and other factors that could control that peak of runoff.
Yeah, and the 2021 heat wave was not going to have the biggest effect in terms of what you could see from the glaciers because it happened so early. There was still snowpack, which would obscure the contrast between the South Fork and the North Fork, but also obscure the impact of the glaciers because everything was snow covered above, say, 1,000 meters. So, the glaciers lost 5 to 10% of their total volume just last summer. And so that was pretty substantial.
Great, thank you. Thank you very much. So we have a question from Taylor. Very interesting presentation, Marie. Do you have any data on the impact of the 2021 heat wave on the North Fork glaciers?
So at this point, it's just the mass balance, and we could see that volume loss of 5 to 10% depending on which glacier. I think as we go back this year, we'll see what the impact was in terms of aerial extent of the glaciers, which is a really key factor for glacier runoff. So we'll be back there in 2 months.
Awesome. Thank you very much. Okay, great. Thank you, Murray, for a very interesting presentation. So for the sake of time, we have to move on. So here is our next presentation by Michel Weber. Talking about multi-method approach on inventorying rock glaciers and features of interest in Banff and Jasper National Park, Alberta, Canada. So Michel, please share your screen, and we're looking forward to your presentation.
Yep, just 1 second here.
Presentation of the session. And our last presenter for this session is Martin Holtzley. Martin will talk about cryospheric observations and modeling for improved adaptation in Central Asia. Martin, over to you.
Thanks very much for the introduction. I would like to welcome you for this short presentation. My main goal actually is today to show you a little bit the work which we are doing since many years now. So we started in about 2010 in Central Asia to do some sort of a cryospheric observation site. And I want to show you today a little bit, some results, but also maybe some problems which occur if you work maybe in Central Asia. So first of all, what I think is important, we already saw one talk of Central Asia before in the poster, is that actually Central Asia is a region which is really suffering water, and the main water actually is coming from the mountains. So we have two big mountain ranges there. It's the Tian Shan in the north and the Pamir in the south. And then we have, of course, the rivers coming out of that. It's mainly the Sur Darya and the Amu Darya River, which actually flow down in direction of Aral Sea, which is more and more dry, as we all know, also see on this picture now. So what is important actually is that the people in the future, and with the reduction actually of the cryosphere, particularly of the glaciers and the snow cover, will probably suffer in different regions in Central Asia, actually to have enough water for the longer term period. At the moment, I think there is still a lot of glaciers available there, and there is also, we can see that also in the field, there's high water also in summertime. But for the adaptation, it's important that we develop actually methods, and to develop methods where we can use not only the remote sensing data, which is very important for the future, I believe, but we need also in situ measurements where we have the possibility actually to calibrate all our models which we use in the future in connection then also with remote sensing data. What I want to show with this graph is very simple actually. So to say that some of the observations and the monitoring is based on the data. And of course, data today we have, as I said, by remote sensing, but also by in situ data. And one of the biggest problems in Central Asia is actually that was the collapse in the 1990s of the Soviet Union actually. And after this collapse, in all countries, more or less, all the observation sites completely collapsed. So we have had no observations, for example, in Kyrgyzstan or Tajikistan, and also in Uzbekistan about cryospheric monitoring. All these networks completely collapsed. And this collapse actually was in a period of about, more than 10 years. So we started 10 years ago with new measurements where we started on all glaciers actually, which had already long periods of measurements like Golubin Glacier in Kyrgyzstan or also Abramov Glacier in southern Kyrgyzstan. But important to say here again, the observations, this is really our tough goal, which we want to succeed in the future, because many of the informations we get afterwards also for the adaptation strategies, they really base on these observations. And therefore, actually, we started with the glacier monitoring, as I said before, 10 years ago, and we set up a cryospheric network for glaciers now in the countries of Uzbekistan, Kyrgyzstan, and also in Tajikistan. But now we have already introduced that, and at most places now, the local people already started to do their monitoring on the glaciers. And we want to increase that now also to the other cryospheric observation sites like snow monitoring and also permafrost monitoring. So to show you now a little bit the challenges if you are working in Central Asia is actually the problem that you can see that we have several challenges. One of the major challenges is actually that we have some sort of instabilities between the countries there. For example, Kyrgyzstan and Tajikistan has just recently, 2 years ago, closed the borders. So actually we cannot easily transfer between the countries, which makes our fieldwork normally quite complicated. And then, of course, in addition, we had the complications, for example, of Afghanistan, which is very close to these Central Asian countries and makes also the fieldwork partly in southern Tajikistan not very easy. And then in addition, of course, as you all know, we had also the COVID crisis actually making all the fieldwork even more complicated. But then what we also try actually, and what is one of our major goals, and I think for GLACIER we already succeeded quite well, we could actually start to improve the capacity building and the cooperation with these people in the different countries. So really in Kyrgyzstan, we started in 2010 to educate people. And then after education, of course, we had to look that these people also come in the hydrological networks or in the research institutions, that they could do actually this cryosphere work on the different glaciers. And for this actually, we worked every year with many of these younger students, but also older people, but mainly younger students, to bring them actually into the system. And important is also that we also try newly to empower young female students also to come into the system, because this is one of the biggest problems at the moment, that we have more or less only male students there which do the fieldwork, but we also want to increase now the female students in our observations. Then another problem is actually the access to the field. So, you know, during the Soviet time, normally they had helicopters could easily transfer actually into the field and do their measurements. Today, this is not anymore possible because of the costs. So actually, normally the access to the field is quite difficult. And of course, it's not only the access to the field, it's also that we have to find the old data, because there is a lot of old data. But to get the old data, this is sometimes quite complicated for the different monitoring sites there. And then we have also some scientific challenges. I have not enough time really to go into detail of that, but we know actually we have several studies, particularly remote sensing studies, and we still have quite considerable differences and uncertainties. And this is really one of our main objectives, that we want to reduce actually these uncertainties. And this including actually also the in situ measurements, that we can improve actually then also the uncertainties for the larger scale studies, which we want to do also for these regions. To show you a little bit that we care actually at several places, we have really large uncertainties, and particularly this is important if you use models. Today, if you use models, normally we have the problem actually that we sometimes use reanalysis data, as we have heard. So many people in the world using reanalysis data. If you use that, for example, here in Switzerland, where I live in the Alps, then it works really fine. So because we have very good reanalysis data. But if we do this work in Central Asia, we experience now that we have big problems, because reanalysis data are very often very bad actually to use them in these cryospheric mountain fields. And then, of course, I think the most important thing is the long-term financial support. To make cryospheric observation, as we heard from Mauri before, sometimes we need many, many years, 20, 30, 40 years. And to support that on a long term means that the country has really to support these measurements on a longer term. Just to show you the table here on the top, you can see the measurements. I just compared now the European Alps with the Tian Shan and the Pamir Mountains. You see we have in a surf, you see here the glacier area actually of Europe, which we have for example, 2,000 square kilometers. In Tian Shan, we have about 12,000, and also in the Pamir. But if you look to the mass balance measurements, for example, today we have 7. Actually, some years ago, we had only 1 glacier. It was Tuyuksu Glacier in Kazakhstan. And then the same is also for permafrost boreholes. In whole Central Asia, there is only 1 permafrost borehole in Kazakhstan. In all other countries, we have no boreholes. And the same is also the case actually for in situ measurements of the snow cover at the moment. So this means really that we have to enforce that. If we compare that, for example, to Europe, where we have only on a smaller scale 64 measurements of mass balance and over more than 40 boreholes to measure the permafrost temperature. So we see really the big differences. And we have to work hard actually to bring these large mountain scales like the Tian Shan and Pamir also in our observation network. Okay, so shortly, just I want to show you what we did actually. We have not so much results from our snow and permafrost monitoring because this we actually just started now. But in Central Asia, I can show you what you see on the map, that we have now a nice glacier network actually for the different regions, which we built up in the last years and which we continue. You can also see that what we also try is also go back, like the ECVs actually also recommends that we try also to reconstruct some informations from glaciers. So for example, for the parts where we have no measurements, so for example, from the 90s to about 2010, where we have then again direct measurements. And this we not only do on these individual glaciers, we also try, for example, to get more information about the accumulation rates, also to see if we there maybe see a change in an increase of accumulation rate, which is very often actually sad also for the Central Asian countries. Then, of course, we do also local measurements, that we use aerial images to do volume or mass change measurements in this area for individual glaciers, that we have some very accurate measurements for individual glaciers, which we can also use then to compare with the large-scale remote sensing studies. And then maybe one of my last slides actually to show here are two images where I believe this is really important, that we observe also the regional. So we actually use remote sensing, but calibrate it with in situ measurements from the local measurements to see actually where our glaciers, which we observe, are. So for example, if we go to here to the central Tian Shan, actually, where we have several measurements like Golubin Glacier or other glaciers, we can actually see where our observations really fit into the different observations of all glaciers if we compare them. So we can do some sort of an evaluation if our measurements are in which regions they really are located. And for that, I think we can also improve then on a larger scale and look then with remote sensing, but calibrate it actually with in situ measurements if we get some more precise results actually for the larger scale. So I just want to summarize. I think what is very important actually, that we have to increase actually our observations of the monitoring, not only for the glaciers as we did in the past, but also for the snow and permafrost for the future. And that, of course, that we deliver this data to the all researchers, that they can actually work with this new information and improve actually maybe their models or their studies. And the second one is that we really have to work hard on the capacity building that we have in all these scientific research of the cryospherics observation, that we have people on a local scale that can do really these measurements. Thanks very much for your attention.
Thank you. Thank you very much, Martin, for this great presentation. We do have time. There is one question in the chat by Michelle. Thank you for all of the hard work and initiative that went into the organizing, not only the conference, but the session. Okay, so it's basically a comment for the whole session. So thank you, Michelle. So do we have question for Martin? It seems, Martin, a very large and long project. And it's basically, I mean, you listed the challenges. It's not easy to collect all the data from all different countries. You mentioned about capacity building and collecting data from the local people. I'm just wondering if you have any training plan for these countries that you can train them and then build the capacity there. Do you have such a program with this project?
Yes, actually in all this project, we have this program. We try to do the capacity building, first of all, in the individual countries sometimes, but sometimes also we make larger summer schools where we invite all the regional countries. So these are mainly Kazakhstan, Uzbekistan, Tajikistan, and Kyrgyzstan. And then we have normally 2 or 3 people of these countries, and then we train them actually in summer school. First of all, do the observations directly in the field, but also afterwards, how we do the analysis then back in the office so that they really try to do their own work at the end in their countries. Yeah.
So basically with this trainings, you're targeting specific countries that you need more data.
Yeah. And this is actually, you know, the hard stuff actually at the work is to really convince also, you know, the important stakeholders in these countries, also the politicians actually, that they see, okay, this is important. We have to support these investigations at certain places now on a longer time range. You know, this is very important. Because, you know, sometimes if you just start with a project and it is 3 years, and then, you know, after 3 years, maybe the people are not well trained and maybe the initiative is not so good, and then it stops again, and then you do not have again the data. So this is really the tough work actually to do this on a longer term. And I think where we worked, and I think in the GLACIER, it somehow really worked, particularly in Kyrgyzstan, where we started at the beginning. We have now there the own people doing really their training. They go on by their own on the glaciers, so they have more or less not much support now from our side. Of course, we help them if they have some troubles or something in the analysis, but in general, they do now their own work actually on the glaciers. And for permafrost and snow, we start now to do this, this capacity building now with new people working then in these areas.
Yeah, with this huge cost of field work, especially in glacier stuff, I believe this is the best approach to go forward for sure.
Yeah.
Thank you very much for your great presentation, and I will thank all the speakers for your great presentations, keeping the time, so we were right on time, and for our audience for your great questions. So with that, here we're closing this session, part 1, and we will see you all hopefully back at 2:55 p.m. Eastern time. So we will continue with the great list of presentations and posters. So there is a plenary happening at 12:30 p.m. Eastern time, and Integrated Canadian Science Addressing Global Agenda 2030. So looking forward to see you all at 2:55. Okay.